Thank you. So I am here again. For those who were not here 1 hour ago, I am a researcher at IBM Research, and I will present now another piece of the puzzle of this epochs project that we are leading at IBM. So I will very quickly skip this acknowledgement, same acknowledgement as before. So same people, thank you to all of them. In the interest of time, I will move forward. So again, I mean, I have said this already, and at this time of the day, I think I have already seen maybe 4 or 5 talks trying to motivate this idea of hardware specialization, right? Heterogeneous chips. So I don't need to go too much in detail. The hardware specialization era is already here. This is an interesting die photo of a cell phone chip processor, where you can see, for example, that in addition to the traditional general purpose CPU, today you have also GPUs, 1 or more, and you have plenty of acceleration engines for different functions in the cell phone. So this is a very nice example of a highly heterogeneous processor. But I mean, the question is, how do we schedule applications, processes, threads in this kind of heterogeneous chip, right? I mean, it's not straightforward, because the conventional schedulers, like Linux scheduler, is not optimized for that. This is true, right? In order to exploit the characteristics of heterogeneous chips. So we think that there is a need, there is at least a call, to think harder in terms of creating more intelligent and efficient schedulers for heterogeneous chips. And how does that impact on new radio, right? So in my previous talk, I presented this ERA application where I show this new radio AO2.11p transceiver, but in the application there was also a ROS part with multiple blocks doing different things, right? Bunch of stuff. So in general, the message is today's applications are very heterogeneous in their nature. So it's not just about the hardware. The software is very heterogeneous. So in other words, the heterogeneity at software level in the application is driven the need for specialized hardware, right? Actually, in this flow graph, we can see that there are many blocks, and all of them are doing different stuff, right? So if we have to execute this flow graph, we may have already an underlying chip with some accelerators. Let's say we may have an accelerator for the FFT, we may have an accelerator for Viterbi, decoding, we may have an accelerator for other stuff, right? But as far as we know, and this connects, I think, very well with this morning's talk by Marcus, the current version of the new radio scheduler is not aware of this degree of the heterogeneity in the chip, right? Which, if exploited properly, can provide significant benefit in terms of throughput as well as power performance efficiency improvement. Actually, I mean, regarding the new radio scheduler, some prior work, this is another paper from Bastian, have shown that some simple tweakings to the scheduler can already provide some great improvement, in this case for cache effectiveness, right? So we believe that there is room for improvement, for example, in terms of scheduling on heterogeneous chips. And this is also the picture I presented before. I mean, before when I talk about the array, I was moving in this layer. Now I will be moving in this operating system layer, but we are, with this project, we are addressing the entire hardware-software stack in this DARPA DSOC program. So let's go into this idea of task scheduling on heterogeneous platforms. I will present an open source tool that we developed that is called STOMP, which allows us to prototype new scheduling policies in a very easy and fast manner, right? So let me introduce STOMP. STOMP, which stands for Scheduling Techniques Optimization in Heterogeneous Multiprocessor. I didn't want to put the H there, so this is, but I wanted to have heterogeneous. It's an open source tool that allows us to prototype and evaluate new scheduling policies for heterogeneous platform in a very agile manner. That's simple. It's written in Python, and it's very easy to customize. I mean, a STOMP user can very easily create new scheduling policies and plug those policies into STOMP and evaluate what happens if we want to schedule, let's say, a representative new radio application on a illustrative heterogeneous processor, right? In STOM, there are basically three main elements. We have tasks, which are, as you can imagine, the units of work. You can call them jobs, processes, threads, whatever. And these are the things that are executed on our heterogeneous processor, right? In STOM, actually, we talk about task types, right? This is the most interesting part. We say this is an FFT task, this is a decoding task, this is a convolution task, right? Then we have servers or processing elements, which are these blue boxes here, right? I mean, these are your processing units in your chip. You can have also different types of processing elements, general purpose cores, GPUs, different type of accelerators, right? This is all customizable. And then the most important part is the scheduler, this green box here, which will basically take tasks from this queue and try to schedule them across the available processing elements or servers, right? And what we want to do is to allow the user to write in a very easy manner new scheduling policies that can be plugged into the scheduler for easy, let's say, evaluation. So the task can arrive to this central queue either probabilistically, or we can generate traces of tasks from real executions. Tasks also have some attributes, like, for example, the service time of a given task type on a given server type, right? So we say, let's see, this is an FFT task that has this service time on a general purpose core, on a GPU, on an accelerator, etc. We are also adding support for power consumption, so the task will also have some power information associated. And the most important part is this. I mean, the user can extend the base scheduling policy Python class and create its own scheduling policy in a very easy manner, right? This is the logic that will instruct the scheduler what to do with the task at the scheduling time. So it's a very simple idea, but very, at the end, it's a very useful tool. So how STOM works internally? There are two components. One is the meta scheduler, that red box there, meta. And the other one is the scheduler, this green box here called sched. They communicate to each other through these two queues, a ready queue and a completed queue. And the idea is very simple. Meta basically will do some pre-processing on tasks, let's say, to connect more with what you usually deal with. Tasks can be, for example, new radio blocks, right? So let's say Meta will pre-process the new radio block that had to be executed in the system, and will, for example, track dependencies, and those blocks, those tags that are ready will be put in this queue for the scheduler to place that block in a processing element, right? When the task or new radio block completes, then the scheduler will put that back on this completed queue, so the Meta is notified, oh, this task is done, and can keep tracking dependencies, right? The input of a stomp is all this here plus this here. So the input comes, as you may imagine, in the form of directed acyclic graph, DAGs, right? Where a DAG may represent, let's say, an application, a new radio flow graph, and the nodes are the task or the blocks that we have to execute. So as I said, Meta does some pre-processing on this task. One interesting thing that Meta does is to compute the rank associated to each task, to each new radio block to execute. A rank is basically a metric that tells us, I mean, how fast we should execute that task, right? So high rank means we have to execute this very fast. I mean, but there is maybe some real-time constraint that we have to meet. Lower rank means maybe we have more slack, we can wait a little bit more. So basically, the tasks are ordered in this ready queue by rank. How do we compute rank? That is implementation specific. The user can define what rank means in he or she specific implementation. But usually, rank is a function of the task priority, as well as the slack, I mean, the amount of time that the task has to complete, as well as, for example, the task worst case execution time, which usually is running the task on the worst processing element, let's say the CPU core, right? So this is one possible formula for rank. Could be many others. And also Meta can, in some cases, we can enable this feature that if a DAG didn't complete on time, if the DAG missed its deadline, then Meta may decide to drop that DAG completely in order to reduce traffic and give more chances to other DAGs to complete on time. So we have also that option available. So the scheduler, which is the other box in this diagram, is where, as I explained before, is where the user will plug his or she scheduling policy, right? So this is very easy, actually. I mean, the only thing we have to do is to extend this base scheduling policy Python class. More specifically, what we have to provide is an implementation for this assign task to server function, which basically tells the scheduler what to do with tasks in the ready queue at scheduling time. In this, for example, in this very simple implementation, this is just for illustration purposes only. What we are doing is we are taking the task at the head of the queue, this one here, right? And we try to place that task. I mean, the scheduler will try to place that task on the fastest processing element, let's say an accelerator. If that processing element is not available, then the task will remain in the head of the queue. This is what is implemented here. Very easy stuff, just for illustration purposes only. We want to make more intelligent scheduling policies, of course, right? Then we can, of course, easily configure Stomp with different parameters. For example, we can indicate what scheduling policy we want to use, right? So in this case, we are saying Stomp to go and look for a file called, a Python script called simple policy version 3 under the policies folder, right? And then we can configure the number of processing elements. We are saying that we have, in this example, 8 general purpose cores, 2 GPUs, and 1 FFT accelerator. And then we define our tasks, right? For example, we say that we have tasks of type FFT with different service time for the different processing element types. And we may have other type of tasks also, let's say decoders or convolutions or whatever, right? So it's very easy to configure. Let me show a very simple example of how this works, right? Let's say we have an input DAG of 5 tasks of 5, let's say, new radio blocks, which is that one showed there. And then what Meta does, the Meta scheduler does, is try to determine what is the deadline for this DAG to complete, which in this case is defined as the execution time of the longest path, the critical path. In this case, that is 0, 1, 3, and 4. In the worst case, meaning running on, in this case, on the CPU. So for that critical path running on the CPU, that is around 1,100 units of time. By the way, Stomp is unitless, so the user defines the meaning of a unit of time. So then at time 0, at the very beginning, Meta will take the root node there, and will compute its rank using whatever formula for the rank has been defined. In this case, we are using that formula, and for this specific initial case, the rank is very high, it's infinite. I don't want to go into much detail here because of lack of time, but for that first node, basically, Meta will take that node, will compute the rank, will put it in the ready queue, and that task will execute after the scheduler places on a processing element, that task will execute. Let's say that since everything was available in the chip, that task was executed not in a CPU, but on an accelerator. So instead of taking 500 units of time, it took 10 units of time, which is good because that gives us some, let's say, time back for the rest of the task in the DAG, right? So at time 10, after that task completed, then Meta will update the rank of task 1 and 2, which are the ones that now are ready because they satisfy their dependencies, right? So using the same formula as before, we compute ranks of task 1 and rank of task 2. And in this case, in this simple example, rank of task 1 is larger than of task 2. So the next one that will go into the ready queue is that task number 1, the decoder there. That will be scheduled by the scheduler based on the scheduling policy that the scheduler is using at that time. And this process continues for all the tasks in the DAG until the full DAG completes, basically. In Stomp, we also support multi-DAG execution, meaning that we can have multiple of these DAGs running at the same time, right? In that case, basically, the Meta scheduler will keep track of dependencies across all the DAGs and will update the ranks also across all the DAGs at the same time. There is no, let's say, sequentiality in that regard, right? But this is another feature of Stomp. So let me show you some preliminary numbers that we have generated with STOMP for an illustrative, let's say, new radio example. So what we did is we defined a trace of DAGs with 1,000 DAGs, right? Let's think about these DAGs as 1,000 new radio flow graph, right? In this case, two different types, with 5 and 2 tasks, with 5 and 2 blocks, right? So very simple ones. And we assign priorities to these DAGs, 1 and 2, randomly. And we define the deadline for a DAG to complete, as I explained before, like the length of the path, the critical path running on the worst case processing element, in this case the CPUs, right? And we find three simple task types: FFT, convolution, and decoder, right? And the metric of interest is the number of DAGs, let's say flow graph, that met their real-time deadline during execution, right? So we created 5 simple scheduling policies. Well, simple, I mean, starting from simple ones to more complex, more interesting ones. TS1 and TS2 are non-blocking scheduling policies, which basically means that the scheduler will look within a window of tasks in the ready queue, not just the one in the head of the queue, but the window. And we'll try to schedule all of them, even if one before couldn't be scheduled because, I mean, there was no available, let's say, accelerator. It will keep looking in that window. This is why these two are called non-blocking. And TS2 is a variation of TS1, where at the scheduling time, not only the scheduler will traverse that window, but will keep in mind what was done with the previous task in that window. So we know what was the scheduling decision for the previous task, and that allows us to make a little bit better scheduling decisions. But in these two cases, meta is only used for dependency tracking only, right? There is no rank computation in this case. So then we have like an improved version of TS2 using meta for both dependency tracking as well as rank computation, right? And we have these 3 versions, MS1, MS2, and MS3, where basically the difference is just the formula that we use to compute the rank, right? So for example, in MS1, we use the task deadline, its average execution time across all the available processing elements, and the priority. In MS2 is, again, we compute the rank as a function of the task deadline, the maximum execution time across the different processing elements and priority. And MS3, the rank is computed as a function of the available slack and the maximum execution time as well as the priority. So 5 different policies. Let's see what we get. So what we get is something that what we expected. MS3 is the most interesting of these 5 policies because it's the one that allows DAGs to complete in time in the most cases. So this chart, what is showing is the percentage of DAGs, let's say radio flow graph, that complete within the deadline as a function of the 5 different policies for different arrival times of DAGs. And as I said, we have 2 priorities of DAGs, right? Priority 1 and higher priority 2. So for example, what we see here is that MS3, for this particular case, allows all 100% of the high priority DAGs to complete within their deadline, right? Compared to the other policies, which is good, right? And this is by the way, it's a very simple policy. I mean, we are not doing, it's not rocket science, right? I mean, some simple tweaks can help us to optimize the scheduling. So let me, I think I have some time. Let me show this. This is a video recording of how to run STOMP. Very simple also, nothing that will impress you. But it's just a 2-minute video. As I said, we use these traces of DAGs. So we have a script called trace generator that will generate a synthetic trace of DAGs. In this case, we have 1,000 DAGs that arrive at different arrival times. So the second field is the DAG ID, and this is a DAG type. So we have 1,000 DAGs that arrive to our simulated system, right? So synthetic, very simple trace. We can generate that from real execution too. Then we configure STOMP using this JSON file. We indicate, for example, the policy that we want to use. We can indicate, for example, well, as I said before, I mean, what processing elements we have in our system. And lower below, we also indicate the different task types, right? FFTs, convolutions, and I think we have also something else, the color. So one way to execute the stomp is with the stomp main script. But then we have a more convenient script called run all, which will run multiple configurations of a stomp that can be easily defined here at the beginning of that script. We can say which policies we want to evaluate, what is, for example, the arrival times, etc. So this script will execute multiple combinations at the same time, which is very convenient. So what the video is showing is just how do we call that script. We can indicate, well, verbose, dump everything on a CSV file, and this is the input DAG trace that you have to use. So right now, it's in this example, it's only one combination. So we are actually executing one instance of a stomp and passing all that JSON string to configure that specific execution. So it finishes and it generates an output file that we can easily process with another script that we call collect py that will just parse the output, and in this case it will print out, for example, we can print other things, but in this case the average response time of all the DAGs for that specific simulation, right? So very simple. I mean, you can run this learn and how to run this in 5 minutes. I mean, it's extremely simple. So so let me wrap up here. Stomp is an effort that is in active development, right? And we are considering thinking about some new features to be added. For example, like support for more complete input trace formats. We want to also generate more statistics. I think some interesting things that I want to mention is that as part of these new features that we will incorporate, we will have support for power modeling. It's not just about performance throughput, but also power efficiency. And something that I think we think is very, very interesting. We want to explore more machine learning like scheduling policies, right? The 5 policies that I show in the example below are relatively simple heuristics. We think that we can exploit some machine learning techniques to do even better. Not necessarily we have to go to complex deep learning, right? We can talk about, I don't know, simple decision trees, for example, right? So we want to go into that area. And I am emphasizing this because this is some interesting area where everybody can eventually collaborate or contribute if interested, right? So we believe that the machine learning can provide some very good benefits when it comes to scheduling of tasks in heterogeneous platforms. So, and we want to move from the abstract to the more concrete. We are adding support to characterize real applications, like, for example, real radio workloads, and generate DAG traces from those real executions instead of just creating synthetic DAG traces, right? But Stomp is already a very nice tool that provides plenty of opportunities to explore the problem domain and generate conclusions. So please, I mean, check it out and play with it and provide your feedback. You can check out the dev branch if you want, which provides more leading edge features. So please let us know if there is any feedback that you can provide, or any way that you think you can contribute or collaborate. So thank you very much. You won't see my face again today. This is my last talk.